Now I'm going to talk about in detail about the static friction and kinetic friction and eventually their formulas. Friction general formula, it is represented by F sub F. The general formula for the friction is mu times F sub n, and F sub n is the normal reaction, right? Friction force is mu times Fn, F sub n is the normal reaction, and the value of mu is something which depends on whether that's a static friction or a kinetic friction. By the way, what is mu? Mu is the coefficient of friction, which is actually surface dependent. So don't worry about this thing. This will be given in the question that, okay, the block is, let's say, on a sand, this is the mu. Block is on a smooth floor, this is the mu. Block is on a stone marble, that is the mu. Or block is on, let's say, a very smooth surface with bearings, this is the mu. So this mu is the coefficient of friction, of which the value will be given in the question, and Fn is, of course, the normal reaction. Fn is the normal reaction, and Ff is the force of friction, Excellent. Like I said, there are two types of friction, so there are two types of mu as well. For the static friction, the mu is represented as mu sub s, and for kinetic friction, the mu is represented as mu k. There is a very important difference between static and kinetic, which in a way I have already mentioned. However, I will talk about this in detail now. If you remember the example of the kid's mom and dad, initially till before the time when dad came in, if you notice carefully, the force of friction was adjusting itself. It was 2 Newton, 5 Newton, 12 Newton. So that static friction, because the block is not moving, has a tendency to adjust itself up to a maximum value. This is a really important difference between static and kinetic, because static friction can adjust itself. This can adjust itself to a maximum value of mu s times F sub n. Why mu s? Because mu s is the coefficient of the static friction, which I plugged in over here. So mu s times Fn is the maximum value of the static friction to which it can adjust. However, kinetic friction is a constant force which cannot adjust. It only comes into action when the block is actually moving, and its value is mu k times normal reaction. And please remember, most likely the value of mu k is going to be slightly less than mu s, which eventually means that the kinetic friction is going to be slightly less than the static friction. This is a really important observation which you have to keep in mind, that the static friction and kinetic friction are not equal. The value of the kinetic friction is slightly less than the value of static friction. And that's why when the dad came in and he applied 20 Newton force and the block started moving, the friction will not be 12 Newton, because that is the maximum static friction. The force of friction will be somewhat less, maybe 11 Newton in the opposite direction, somewhat less, but it will not be 12 Newton. Right. So this is a really important clarification, or the difference between the static and the kinetic friction is that the static friction can adjust itself according to the external force, obviously till the point when the block is not moving. As soon as the block starts moving, kinetic friction acts, which is a little less than the static friction. Right. I hope this makes sense. Next, we are going to make a chart on the friction versus so I'm going to come here. I'm going to first make a chart on the friction versus the external force. So this is where our axes are. Over on the y-axis, I have my force of friction. Over on the x-axis, I have my so-called external force, you know, the with the kid or kids or mom and dad are applying. This is the external force. Obviously, initially when there is no force, there is no friction, because obviously there is no slipping tendency. And as soon as the force external starts increasing, the friction force also starts increasing till 12 Newton, if you remember, hypothetically. So it sort of increases like this. After a time, when dad comes in, there is a sudden drop over here, and then the friction becomes constant. Why? Because this is a kinetic friction, and kinetic friction is always constant. So this maximum value is considered as mu k times mu s times normal reaction. So this is the maximum static friction. However, this region is the kinetic friction, which is always constant. This is the kinetic friction, which is always constant. So till this point, there is no sliding. Till this point, there is no sliding. But eventually, if we increase the force even further, the sliding starts occurring over in this region, and the friction just remains constant, which is slightly less than obviously what the other value is. I'll just also indicate that this value is mu k times normal reaction. All right, I hope this figure makes sense. This is really important and really popular. Another version of this figure is given over here. This is just an example that this is the static friction. I hope this makes sense now. This is the static friction, kinetic friction, sliding, no motion. This is the maximum value, obviously, of mu s times Fn, which is eventually equal to, you know, this one, because they are equal and opposite. These are some hypothetical values which they have taken. So I just thought that you should see that how this looks in a book as well, rather than me only drawing it, so that you you know, you get a feeler that okay, this is how it is made, right? And last but not least is these are the coefficients of friction for a few surfaces. You are not supposed to remember it. This is just for you to see how mu s usually looks like, and mu k is always a little less than mu s. For example, you take wood on a wood, because blocks are maybe usually made of wood. So the block of mu s is, for the wood on wood, the mu s is 0.4 and mu k is only 0.2. So mu k is a little less obviously than that. So don't worry about this. This will be given in the question, and when in the next lecture we'll solve. In fact, I have 2 lectures on questions on friction, level 1 and level 2. So we're going to do a lot of questions on friction, so that you get a gist of, you know, how to eventually use everything which we have covered in the friction. I hope this makes sense, and I'll see you in the next lecture. Bye-bye.